Hello, everybody, and welcome to the exam school. My name is Pumi, and yes, you are joining us live right here on the show that is proudly sponsored by MTN SA Foundation and also endorsed by the Department of Basic Education. Right here on the show, we are still running a competition, which is the K53 hashtag Be a Bright Spark. So I just want to know from you guys, have you tried to enter the competition? Because if you haven't, hey, you are really running out of time because the show will be closing on the 15th of November. So please make sure that you are part of this competition because you could be winning yourself a Chevrolet Spark L. So all what you have to do is, one, make sure that you buy the application from Samsung, from your Samsung Galaxy application, or you can also go on Google Play Store. That is where you can actually get to buy the application, or you can better yet to buy the actual book from any retail store. Keep the receipt so that you can ensure that you can win, because if you don't have your receipt, you actually won't get to win. So make sure that you keep it with to prove that you purchased the book. And of course, at number 2, you can also like us right there on our Facebook page. It is facebook.com/learn extra or facebook.com/Safeway K53. That is where you can get your entry form and then enter your details, and then soon after that make sure that you share with all of your friends, because through doing that you could be earning yourself, not even could, you are definitely going to earn yourself an extra entry. Right now, guys, let me just introduce you to Tracy, who is joining us in studio. Hello, Tracy.
Hello, Pumi. How are you?
I'm good, thanks. How are you?
Good, thank you.
I'm good, thank you.
Excited?
I'm very happy and excited. The matriculants have started to write their finals and I'm feeling very confident about them, aren't you? You are, I know you are.
Sometimes, sometimes not. You know, you walk when you matriculate, and some of them you can see you've studied, some of them. But looks like it's going well, so we'll see. It's all about tomorrow, though.
Yeah, hey. Guys, I can really advise you to not panic. Just make sure that you join us, go through the show with us, and definitely ask all of the questions that you have, because we are definitely willing to answer as many as possible, because we are also going to be having a special show where we have it just for you guys. So make sure that you keep in touch with us, bring all of those questions so that you can be ready to tackle that paper. Right now, Tracy, are you ready to...
Oh, I'm good. I'm good. Let's jump in there.
Awesome stuff. Enjoy.
Guys, thanks. Guys, we obviously can't cover everything in this hour and a half, okay? Remember, your paper is made up of your mechanics, your wave, sound and light, and of course your electricity. So I've tried to pick out a couple of questions where I think you might be taking the most strain and where you're probably struggling the most, either from a maths point of view or a conceptual point of view, and those are what we're going to get through. Don't worry. Eventually, the link will be on Facebook for you to get the notes. There's 4 questions I want to try to get through in this hour and a half. But if I don't, it's okay, because through a whole bunch of circumstances, you get an extra hour of a live science show after this hour and a half. So from 5 to 6, there's more science, where also we'll deal with any questions in sections that I haven't actually managed to cover. Okay, so hang in there. Go with it. Okay, I know it's been a busy week for a lot of you. Last push for physics. Okay, so let's jump in there. And what we're going to do, guys, is we're going to start straight away. And basically, I'm looking at mechanics, electrical circuits, and the photoelectric effect, okay? I didn't do anything with wave, sound, and light. Remember, pretty much wave, sound, and light for you guys is the photoelectric effect sort of goes into it, but it's Doppler. And Doppler, you know, we've done that lots, and hopefully you guys are doing okay there. So we're going to start with mechanics. Now, this question was actually sent to us on the helpline by one of the mindsetters. So thank you very much, whose name I can't remember right now because I should have written it down. And it's actually a really, really, really nice question. So we're going to jump right in on this one. And it says to us that a brick A of mass 2.5 kilograms. So remember, the best thing to do when you write an exam, guys, is to write on your question paper, because it's all about interacting with it and making sure you know what they're asking you. So brick A has a mass of 2.5 kilograms. So I'm going to write that in there so I remember. It is at rest on a 1 meter long frictionless plane. So this is 1 meter. Okay, and it's frictionless. We like that because it makes our life so much easier. We like that very much. Okay, and it's at 30 degrees to the horizontal. We've got the 30 degrees. A second brick B of mass 3.8 kilograms Grade 12s don't worry about whether you get funny numbers. So if you get strange decimals and you'd rather work with halves and whole numbers, I'm afraid that's not going to happen. So just go with it. I know 3.8 is an unusual mass, but there was probably some thinking in that question along the way. But don't stress about it, okay? At the bottom of the incline, on a flat, rough surface. So over here, we have a rough surface, which means this horizontal section has friction. Okay, there's friction. We might need that later on. So now the very first question says, calculate the speed of the brick at the bottom of the incline when it is released from rest. This question's worth 4 marks. Your mark allocation is always based on the simplest method of calculating of doing the calculation, okay? Now, this particular question, and when I looked at it and I went through it, I went, well, actually, this is such a nice question because there's 2 ways that you can do this question, both of which are perfectly acceptable, okay? Whenever we see a question, and if you read later on in the question, you'll see that actually block A is going to hit block B. Okay, so block A is going to slide down this ramp, get to B, and it's going to hit B. That means there's a collision. Whenever there's a collision, I know momentum's involved. Okay, so that's the first thing I know I'm going to have to use. The trend, grade 12s, is that if I'm going to use momentum, then probably it's going to be connected to an energy conservation principle question. But so my first thought here is to go, well, actually, I can use energy principles to do this. It's a little more difficult, but I can actually do it because there's no friction on this incline. So all I really need to consider is what is the vertical height that A went through, because that's the energy, potential energy that it loses. Remember, when we looked at conservation of mechanical energy, we never considered the path, because conservation of mechanical energy means we're using conservative forces, and conservative forces, it doesn't matter what path they go on. Friction is a non-conservative force, and the path that the object goes on is important with friction. Okay, so there's no friction, so it's a conservative system, which means I can use conservation of energy. Okay, so now we've got to say to ourselves, fine, if I'm going to use conservation of energy, then that means that my mechanical energy at the top, or initially we're going to say top, is equal to my mechanical energy at the bottom. Okay, now mechanical energy means that I've got to use potential energy plus kinetic, and that's going to be equal to my potential energy. Ooh, that's not potential, that's okay. That's going to be equal to my potential energy plus my kinetic. Hopefully you're all with me. So the question is, what's the speed of the brick at the bottom? Well, I know I want V, well, VF actually. So that means I'm going to look for kinetic energy. So now we go this back to here and we go, okay, potential energy is mgh, kinetic is a half mv squared. Okay, and that's my initial, and let's call that initial height. And then we're going to have our we're even learning to write a whole bunch of new ways. Okay. So we're doing okay. Hopefully you all stayed with me. And then we go, okay, well, let's think about what I know. The mass of my object is 2.5. Gravity is 9.8. Ooh, I've hit a bit of a snag, because I actually don't know the vertical height. Okay, this is why this particular method is a little difficult. So I need this. This requires trigonometry, okay? Because this, if you look at it again, and I'll do this in purple over here, ooh, or a dotted white line, either way. I meant blue, and it's a dotted white line again. All right, so over here, there we go. I'm just telling you, the board is just making sure you are all awake today, okay? Actually, I have a right angle triangle. That's 30 degrees. The hypotenuse is 1, and I want to know what is that height. delta y, or h. Let's call it h, because that's actually a better. Okay, so this is h. We're going to need trig here. Okay, so we've got to remember that I'm looking at the opposite angle with the hypotenuse. Opposite over hypotenuse is sine. So sine 30 degrees is equal to my height over 1 meter. So actually my height is equal to sine 30. And hopefully you know your special angles. You've written maths already. You did this for Monday. Okay, and sine 30 is a half. So what they're saying to you is that this height is 0.5 meters. That's why they chose the 30 degrees, by the way. Okay, it's not as random as it sounds. So over here, when it comes to my height, I have to work it out. So let's put in sine 30, just in case we didn't know that it's a half. It starts from rest at the top. That means initial kinetic energy is 0. It hits the bottom of the slope. It now has 0 height, which means final potential is 0. Okay. Gets to the end. I know my mass is 2.5, and I want VF squared. Okay. So what we get here, and I'm going to show it to you because I want you to see the calculations. So I'm going to go 2.2. Oh, that's right. I need to switch this off. So we're having a bit of a malfunction. Well, the board's having a bit of a day, just so you know. Okay, there we go. Hopefully now the board will listen to me. So 2.5 times 9.8 times sine 30. And that gives me 12.25. Okay. 12.25. That's good. Okay. I hope you know that if we go a half, well, it's a half times 2.5, so let's do it anyway, so make sure everyone knows where I'm going. So 0.5 times 2.5 gives me 5 over 4, which is 1.25. Okay. 1.25 VF squared. Okay, so that's quite nice. Now it's just solving for VF. So what I'm going to do, and I would do this in one step because here, look at that. I just want to move this in a bit. There we go. So I'm going to go 12.25 divided by 1.25. Okay, that gives me 9.8. It's a very strange number for VF squared. Okay, so VF squared equals 9.8. It looks almost like acceleration due to gravity, but we're not done because actually I need the square root of that answer. So my square root of my answer is not that, it's 3.13. Okay, please don't forget to get the square root of your answer. Okay, it's quite easy to leave it as 9.8 because you sometimes forget about the squares, all right? So this first method is by using conservation of energy. This, and the reason why I started there is because I know, because I've read the question and we went on, there's going to be a collision, okay? So momentum and conservation of energy often go together. But I said to you that in reality, there's actually a second way we can do this. And this is where your understanding of the work energy theorem becomes very, very important, okay? Because this can now be done without having to calculate the height at all. Because my second method says to me that if I take the work net, okay, net work done is change in kinetic energy, okay? Net work done means that I need to take my net force times by delta x times by cos theta. Change in kinetic energy means kinetic energy final minus kinetic energy initial. Now my question becomes, what is the net work? Well, it's a frictionless surface, so we know there's nothing pushing it up. What is the force that's pulling block A down? Well, it's gravity, okay? Now, gravity, if we go a little bit further down, let's go over here. So if we're looking at our block, okay, gravity acts vertically down, and what I actually need is my my parallel component, okay? Because I'm going to consider the component that's pushing the block down the slope. That angle there is my 30 degrees. That's the same as the angle of the slope. Now I'm using the opposite side, okay? My opposite side means that I'm using, I was going to make sure I get the right one, sine, okay? So remember, and I'm just going to do it over here, F net for this particular question is going to be FG parallel, okay? Oh, that's not, that FG parallel, okay, is equal to FG times sine theta, okay? So that means if I now change my equation, and all I'm doing now, grade 12s, is I'm developing my equation. FG sine theta means mg sine theta, because Fg is weight is mass times gravity, delta x, and I'm going to do the substitution in a second, cos theta. That looks horrific. My final kinetic energy is what I'm looking for. My initial kinetic energy is 0, so I'm going to leave it there as 0. Now it's a substitution problem. So this is 2.5 times 9,8 times sine theta, okay? Sine 30, sorry. Let's just go back here. That should be sine 30. All right. Delta x, now I'm look at everything parallel to slope. Delta x is 1 cos 0 degrees. Okay, because it's all parallel to the slope here. I'm looking for this part, which is now 2.5 times VF squared. And you know what? You put this into your calculator, and I get 12,25 equals 1,25 VF squared. And if you look over here, that's the same as this line right there. So I'd get exactly the same answer. Okay, so it doesn't actually matter. Both of these methods, either using energy principles over here, this is energy principles, or using the work energy theorem, will be accepted. Make sure you read your question properly because they can specify. Okay, now we've only finished with the first part of the first question, but I'd rather take it slow so you know what we're doing. So I think, Pumi, we're going to take a short break, and then I'll come back and finish this question for them.
Absolutely. Thank you so much. All right, then, guys, let us just take a very quick break, and when we come back, it is all going to be about us revising physical science. We'll see you after this. Welcome back, my sisters. You're still watching the exam school. I'm really enjoying it, and I'm really loving the fact that you guys are really participating. So please make sure that you drop all of the questions that you have so that we can help you in answering all of them, because right here we have Tracy, who is willing to answer any question that you have. Right, Tracy?
That's great. That's also true. And guys, remember, if it's not directly related to what I'm doing now during the show, John's going to try get to them in the next one, okay? So from 5 o'clock. So post your questions. Make use of this time. Okay, guys, the more help you get right now, you know what, I might just, don't give up yet. It's not over until 12 o'clock tomorrow afternoon when you've now finished writing physics. Then it's too late. Okay, but now it's not too late. Let's get them sorted. And you know what? I sat down with one of my learners today, and all it took was me spending 2 minutes with her and explaining something I'd done in a slightly different way than I'd done earlier in the year in class, and it made sense for her now. So that's what we're here for. Okay, sometimes you just need to hear a fresh perspective. Okay, so ask the questions. It's what we are here for. Okay, so post them. And you know, talking to each other is a good idea. So if you see a question you know you can answer, guys, it's a good way to learn. That's why your teachers look like they know so much, because we have to explain it so much. Just saying. Sometimes 4 or 5 times to the same child, but let's not go there. Anyway, moving on. So now they tell you. So we've got the brick. It's the same question. We go to Part 2, brick A now collides with brick B. Collision, yay. The two stick together, that's important. Okay, so the two stick together, they become one object, and then they begin to move along the flat horizontal surface. First thing they ask you to do is state the principle of the conservation of linear momentum. Guys, this is learn work, okay? Up to 10% of your exam, straightforward, learn work. Define, state laws, all of that sort of stuff, okay? So if we go here, and the definition, let's get rid of that because I had no idea what I did there. So the definition is this: the total linear momentum is conserved in an isolated system. So what we're looking for is, number one, linear momentum has to be in there. It's conserved or remains constant is also another way to write it. And what they're looking for has to be in an isolated system. It's got to be closed. Okay, very, very important. Why did they ask you that question? Because they're leading you into 1.2.2. Because in this question, now they say to you, calculate the speed with which the two bricks move along the horizontal surface. So we're going, hang on, let's just have a look at what, earlier on in question 1.1, we worked out that when block A gets to this point, it's going at 3,13 meters. Block B is stationary, so it doesn't have a velocity. Okay. They collide, so there's my collision. Okay, so you can see it's all whatever. And together, they become one object, and off they go. There's a collision, conservation of momentum. That means, okay, there's lots of ways you can write this, but what they're looking for is that the sum of my initial velocity, momentum, is equal to the sum of my final momentum. Total momentum before equals total momentum after. Okay? This line is your scientific principle. Okay? Remember, from here, the next line with the masses and the velocity and stuff all depends on the situation. So we set it up according to the situation. Now, before the collision, there were two separate objects. So we had block A, which has a velocity. We have block B, which has a velocity. Afterwards, they became one. Okay? So we add the masses together, and together they have a final velocity. Now, I'm pretty sure someone is saying, but Tracy, why don't you use the velocity from the top of block A's motion? Because it's too far away. Okay? With the momentum, I'm concerned with the moment just before they collide. Okay, so I'm concerned with this part of the motion, which is why I need to use the 3,13. Okay, also, if I consider A at the top here, A there is 0. The velocity there is 0. It started from rest. So then we're going to get 0 velocity along the way. It all just doesn't work out nicely, okay? This is the science. What's left is maths, okay? So block A was 2.5 kilograms. It was going at 3,13. Block B is 3,8. I'm just going to write it in just so you can see, but it wasn't moving, so it's 0. Could actually leave it out there. Then they become one object. And I want final velocity. Now, I've forgotten to do something really, really important. In this particular question, it doesn't matter, but I'm hoping somebody's going, no, I know what you forgot. I forgot direction. You have to choose a direction as positive, okay? So I'm going to say the original direction of A is positive. Coming down the slope, hits in the ground, and off it goes, okay? There's not too much of a chance that we're going to end up with an answer here where one of them ends up going backwards because they became one object. And for A to be going down the slope, hit B, which wasn't moving, and then go backwards, that's a sci-fi movie waiting to happen. Okay, so we're not going to worry about that. So here we go. So now this becomes a maths issue, as we all know, and I'm going to try very hard. Oh, look, it's. I think the calculator likes me. Shh, don't tell anyone. Okay, so 2.5 times 3.13, and we get 7,825. I'm going to keep the whole number. Okay, 8 to 5, 2,8 plus 2.5, so 2.5 plus 3.8. It's always better to check. Gives me 6,3. All right, so I want VF on its own. So I'm going to go 7,825 divided by 6,3, and we get 1,24 meters per second. Okay, the blocks slowed down. Okay, so A was going at 3,13, and now it's going a lot slower because the mass has gotten bigger. Okay, it's going to take a lot more effort for it to move. Okay, so that was a momentum question because now we have a collision. This is what I love so much about this question. First part of the question essentially was an energy problem, which we could use the work energy theorem for. Second part of the question is momentum. And now we get to the third part of the question. And now they say the frictional force acting on the two bricks is 5 newtons. Calculate how far the bricks will slide before coming to rest. Equation of motion question. And Newton's laws. Because let's just divide this. This is block A and block B. They're going at 1,24 meters per second. We've just calculated that. But because there's friction acting backwards, they're experiencing a negative acceleration, which is going to cause it to have a final velocity of 0. And we're like, oh, look at that. And they want to know what delta x is. Grade 12s. In school time this year, you would have done vertical projectile motion. Okay? Absolutely going to get asked. Just understand that. However, there is nothing to say that you cannot get horizontal motion for equations of motion. Okay? There's nothing in the documentation that says you cannot get horizontal motion. So remember, they can include it. So now you've got to be careful. First thing I'm going to need to do is let's write down what I know. The blocks, now it's a whole new set of values. Well, it's a whole different section of motion. They're going at 1,24 meters per second. They're ending, because they're going to come to rest, at 0. I don't know A. I don't know how long it takes. I don't know delta x, because it's horizontal, but that's actually what I'm wanting. Okay, and I do know that the frictional force is 5 newtons. So, we look at this and we go, okay, finding time isn't really going to help us very much, and there's an equation that doesn't have an acceleration in it that we could use, but then I've got to find time, and to find time I need acceleration, so it's actually just going to get difficult. But I can find acceleration because I know friction, and I know from Newton's second law that F net equals ma. Now we've got to say to ourselves, fine, A and B are sliding along the surface, but there's nothing actually pushing them that way, but there is friction pushing backwards. I am going to take the original direction as positive because that's what I've done the whole way through this question. You cannot all of a sudden decide that the opposite direction is positive. Okay, you cannot change your sign convention. So the only force acting on there is friction. Okay, so essentially, my F net is my friction. My friction is in the opposite direction. My mass, we worked out to be 6,3. And now I want acceleration. Okay, so my acceleration, so this is going to be 5 divided by 6,3. Okay, it's going to be negative. And we get 0,79, but it's negative. 0,79, negative because it's slowing down. Okay, so now I know that that's minus 0,79. And now it's about going, okay, so which equations of motion would I use? Because I don't have time. So we're going to use the equation of motion that doesn't have time in it, which is this one. Vf squared equals Vi squared plus 2a delta x. Vf is 0. Vi is 1,24. A is minus 0,79. and I want delta x. Now, grade 12s, if you get your sign wrong here, okay, and you don't realize that that's got to be negative, you're going to end up with a negative delta x along the way. And with a negative delta x, you know you've made a mistake, because then you're telling me it's gone backwards, which you know it didn't. It went forwards, okay? So now this is just a pure maths problem. So I'm going to go, just so we can be on the same page, 1,24 squared. Okay, which gives me 1,5376. Okay, I'm going to put it on this side, which is giving me 1,5376. Okay, I'm going to have 2 times 0.79, which is 1,58. All right, and from the maths, I've got negatives on both sides, which means now I can just do a nice division. Okay, so now I'm going to go 1.5376 divided by 1.58, and I get 0.97. So delta x equals 0.97 meters. So my blocks go 0.97 meters before they stop. Okay, if your maths is strong enough, you can go from here to here. It's not an issue, grade 12s. This middle step is for you, okay? Please, grade 12s, don't try and be a hero. Don't try and take shortcuts. Do it step by step by step. You have 3 hours. You have more than enough time to get this done, okay? So in this one little question, it's not even worth that much in a grand scheme of things. We covered energy, we covered equations of motion, we covered Newton's second law, and we covered momentum. Okay? Nice question. My kids right now are going, ma'am, don't you dare set us one of those. Well, it'd be fun, just saying. So, grade 12s. I think we can take a short break, and then when we come back, I'm going to tackle a really, really nice work energy power question. Okay?
Oh yes, my setters, also please get yourself a glass of water so that you can always just refresh, because that's what I'm about to do together with Tracy. We'll see you after this. Welcome back from that ad break, Mindsetters. We are still revising physical science right here with Tracy in studio. Tracy.
Thank you. Sure, she doesn't talk very much, does she? Anyway, moving on.
Time.
Okay, so we are doing the question 2 is actually adapted from the Eastern Cape September paper. So it's actually a really nice one. And the diagram below, so this is work, energy, and power, by the way. The diagram below shows a crate of mass 50 kilograms sliding down a steep slope. The slope, and it's all written on there, slope makes an angle of 30 degrees with the horizontal. Brilliant. The motion of the crate as it moves down the slope is controlled by a worker using a rope attached to the crate. So you've got to imagine there's a person over here. Okay, it's a very tiny person. Let's call him a fairy, I don't know. And he's pulling the crate. So he's allowing the crate to slide down the slope, but he's not allowing gravity to do the work, okay? He's saying, fine, gravity's going to pull it down. I'm going to pull it up so that it doesn't go down uncontrolled, okay? So the rope is held parallel to the slope. The tension in the rope is 300, so let's write that in, okay? And they call that FT, so we've written that in. And a constant frictional force of 50 newtons acts on the crate as it slides down the slope. Now we've got to be careful when we look at this question, because the thing here is that there's more than just FT acting on my object, okay? There's friction, which acts upwards. Okay, let's just pretend that's, there we go. And they told me that that was 50 newtons. And at the same time, there's my gravitational force, which is actually the parallel one. That's the one I'm concerned with, the component. Because remember, gravity actually acts down, and gravity is what's going to be pulling it down in the first place. Okay, so this object actually has 3 very important forces acting on it. Now it says, draw a labeled free body diagram showing the forces parallel to the slope acting on the crate as it moves down the slope. Now, guys, first of all, it's a labeled free body diagram, which means you've got to explain your labels. Secondly, it's a free body diagram, which means it starts with a dot. Please, you cannot turn a slope into a horizontal. I see it all the time. Or turn a slope into a vertical, because you can't handle the thing. It just doesn't sit well with you. Whatever way the object's moving and how the forces act, your force diagram or your free body diagram must indicate that, okay? It must do the same thing. So that tells me that my forces for this object must go at an angle, okay? That matches the 30 degrees. Now, by drawing all over here, I've actually pretty much drawn my free body diagram. I've just got to put it all together, okay? So I know, because we said we had tension, which acts up, okay? We said we also have friction, and you would draw those parallel, not quite as badly as I've done. And then, and this is the one that's important, you have FG parallel. You can't call that FG, because I'm not looking at the vertical, I'm looking at the parallel to the slope, okay? This is not fully labeled yet though, okay? That's got labels, but it's not what they want. What you now need to tell me is that FT is the tension in the rope, okay? You need to tell me that FF is friction, and you need to tell me that FG parallel is there's the parallel component, and I'm going to run out of space, of gravity. Compo. I think it's a very good thing I didn't write English today. Component of weight. Let's call it weight. Okay, that's now a labeled diagram. You can write those labels onto the diagram, but you must have it somewhere. Okay? Good. Now it says state the work energy theorem in words. Once again, this is all about learning your theorems, okay, learning your words, your laws, and the net work done on an object is equal to the change in kinetic energy of that object. It's nice and easy. And in fact, you can get it from the information sheet, because when you look at it, it says net work equals change in EK. That's where the equation comes from. Okay, a lot of the times your laws, okay, if they have an equation that is derived from that law or an equation based on that law, the equation and the words in the law will match. So you can actually work them out if you think about it very, very carefully. Okay, so that's the first part done. And we're going, this isn't so bad, we can handle this until we get to this. Okay, so now they say to us, the change in kinetic energy of the crate is 45 joules, okay, so changing EK is 450 joules, 45, 450, I'm just making sure you're all awake, okay, so 450 joules as it slides from the top to the bottom. Use the work energy theorem to calculate the length of the slope. So, we want to know what that is. Work energy theorem says to me I need to use W net equals change in EK. W net, okay, W net equals change in kinetic energy, okay. They've told me what my change in kinetic value is, so that's not an issue here. The issue is that this is also F net delta X cos theta equals change in EK. Now, you are welcome to do all the calculations in one step. Okay, so one big long calculation and then it starts to get like this long on your page. I don't like doing that. Okay, and this is a personal thing, grade 12, so it really is. Your teachers might have taught you something different, and that's fine because it's probably right. But I just want you to listen to what I'm saying. To now calculate F net in here and get the right angle for theta, whether it's 0 or 180, can actually be very, very difficult. So what I would prefer to do is go, well, let's work out what F net is. Okay, so let's work out what my F net is. That also means that I have to make a decision about which is my positive direction, okay? Now, my crate is moving down the slope. Let's make down the slope positive, okay? Let's make down the slope positive. Let's just go with that, okay? That means that any downward forces are positive, any upward forces are negative. Friction acts in this direction. FG parallel is down, okay? FG parallel, and I always have to actually draw a little diagram to remind myself. So there's my 30, it's opposite, that's FG sine theta. Okay, I've got to remind myself here. So I'm going to work out F net separately. So F net, okay, is going to be equal to, now watch what I'm doing, FT, because actually, when we do these calculations, it's a vector sum. Okay, and we add them all together. I've already said now that down is positive, so FT, which is now going to be minus 300, okay, this is going to be minus 50, plus, and I just said it's going to be FG sine theta, okay, so let's just put that in there as well, because it's going to make my life a little bit easier. So this is minus 350, plus, and this is the crate they said to me was 50 kilograms. Okay, 50 times 9,8 times sine 30. Okay, and when I work this all out, I have actually worked it up beforehand just to make it easier. This, okay, let me just show you. It's going to be easier that way. So 50, because this is what I'm doing. I'll get it right for you, I promise. 350, okay, and it's minus 350. Let's do it right. Minus 350 plus, and now we've got 50 times 9.8 times, oh, not plus, times sine 30. Okay, and that gives me minus 105. Okay, now I said down the slope is positive, which means this is actually 105 newtons up. Now, before you start going, hang on, wait, Tracy, wait. The object's moving down the slope. How can the net force be up the slope? Because the net force is opposing the motion. The net force, okay, the guy on the rope, is preventing your object from free falling, essentially. It's preventing the object from being uncontrolled when it comes down the slope. So the man is stopping the acceleration from being 9,8. What am I talking about? Okay, he's stopping the acceleration of the object from being 9,8 meters per second squared. He's making it slower than that. And in fact, he's opposing the motion, okay, which then means for us, now watch carefully as to what I'm going to tell you, because we never, ever put in a negative force into our F net question, okay? So this is 105. Now, I've said to you, down the slope is our positive direction, okay? Now, 105 is pulling up. He's doing this for, what was the distance? They said, what was it? Slope, mass, 50. There was a distance somewhere, and now I've lost it. Oh, that's because that's what I'm trying to find. Hello. All right, so ignore that. So there's my distance. I just want to take some of this off, otherwise I'm going to run out of space. So we're fine with that. But now, guys, we've got to think about this. When I consider theta, I consider it in terms of the motion. Now, my object is going down the slope. My net force is up the slope, which means that this is actually cos 180 degrees. But now what do I put in for delta EK? Because my net force is opposing the motion, it's actually preventing my object from accelerating. So what it's doing is it's slowing it down. So my change in kinetic energy is not that it's becoming a bigger kinetic energy, it's becoming a smaller kinetic energy. So this is actually minus 450. Okay? because it's in the opposite direction, because the force exerted is in the opposite direction, it's slowing my object down, which means my final velocity will be smaller than my initial velocity, so I'm going to have a small number minus a big one when I look at delta EK. Okay? And from here, now it's straightforward. Straightforward, all you have to do is substitution in here. Okay? Well, you have to do some maths. Cos 180 is minus 1. So essentially, I'm going to go 450, okay, divided by, and I'll show you, 105 times cos 180, and we get, and it should have been minus there, so it's 4,3. So delta x equals 4,29 meters. Okay, you're going to need to think about those angles a little bit there, grade 12. So I know that one is a little shaky for us, okay? But we actually do need to just go into the last question for this one, which is actually nice because it's grade 11 work. Now it says, calculate the coefficient of kinetic friction on the crate as it moves down the slope. You know what this has? Nothing to do with the rest of the question. Nothing whatsoever. This is remembering that kinetic friction equals coefficient of kinetic friction times the normal force. Now, I know that friction is 50. They told me that. All right, so I know how much Fk is. Now I've got to do the normal force. And this is when I remember that my normal force acts there. Okay, and your normal force in this case is going to be equal to my perpendicular component of my mass, of my weight. So if my parallel component was using sine, my perpendicular component uses cos. All right, so the normal is equal to the perpendicular component of weight, so that's mg cos theta. I know that friction is 50. I want the constant, okay, my coefficient. So this is now mg cos theta. I just want you to see where I get it from. So that's 50 mu k, and it was 50 times 9,8 times cos 30 degrees. And then to get mu k on its own, all right, I'm going to go 50 divided by 50 times 9,8 times cos 30. Guys, please, calculators are wonderful, wonderful, wonderful things. We love our calculators. I'm actually just going to put it over here, or not, because it's, well, come now. I don't always love our calculators when it doesn't want to listen to me. But so we're going to go 50. Actually, you know, we can use the fraction button. That might be easier. 50, okay, divided by 50 times 9,8 times cos 30. Okay, I'm going to finish my bracket there. Let's go there. We get an equal, and that gives me 0,12. And we're happy with that. It's a coefficient, it's a constant, has no units. We're happy with that. It's tiny, not an issue, okay? Completely standalone question from the rest of them. Do not stop doing a question because you get stuck on one of the parts. Leave a space, go further down, you'll probably find something else you can do. Okay, so we are going to take another quick break, and then we'll come back and do some electricity.
Yippee, I can't wait to do some electricity. Make sure that you join us after this short break. We are still running the K53 Safe Ways competition so that you guys can actually get to win yourself the Chevy Spark L car. So all what you have to do is just to buy the book from the Samsung app or Google Play Store, or you can actually go and buy this book on it at any retail store and keep your receipt as proof of a purchase. So guys, please make sure that you do all of that, and also remember that you can like our page on Learn Extra on facebook.com/Learn Extra and facebook.com/Safe Ways K53. That is where you can get the application form, and then you can fill it in, and straight after that you can actually get to enter. And once you share that with all of your friends, you can actually get yourself an extra entry. So you guys are definitely should be getting posting, or rather entering, because the competition is closing on the 15th of November. Without any further more talking, guys, let's get straight to physical science, because right now we're doing electricity, right?
Yes, we are.
Yeah.
My favorite section.
Awesome stuff.
I love this section. And this is such a cool question. But enter the competition. Who doesn't want a new car? Seriously. Especially as you go into varsity next year. New car. Very important. Okay, so guys, I love this one. It's from the Metro North Common paper from this year, from their prelim paper. And it says to us, and it's such a nice question, that internal resistance is going to get asked. It's a guarantee, okay? Grade 12 learners are conducting an experiment to determine the internal resistance of a battery. Okay, great. We've got internal resistance. I know that makes you want to cry, but it's great. We love it. The learners were divided into two groups. Group 1 used battery 1 with an internal resistance of R1. So there's my group 1 graph, okay. Group 2 used with R2, so that's easy. So two different batteries, which means they have two different sets of internal resistances. The results of the graph are shown in the graph. The results are shown in the graph below, so that's great. And if we look at it, we've got two different batteries. When we look at the start of this, we got to look at what this graph is actually telling me is both of these batteries started with the same EMF, okay? Because when we're looking at a potential difference versus current graph for a battery, that starting voltage over here is the EMF, because here there's no current. So that means both of them started with an EMF of 12, okay? Then, as we look at the gradient of the graph, the gradient's actually quite important, because remember, R equals V over I. So the steeper the gradient, the bigger R is, okay? And that would probably be your internal resistance. But let's just go through the question and see what it says. The first thing they ask is explain why the voltmeter reading across the battery decreases as the current increases. Use appropriate equations in physics in your explanation. Now guys, what they're asking you is, and remember, in a question like this, you would increase the current or decrease the current in the circuit by changing the resistance in the circuit, okay? And that you would do with the rheostat. So they're changing the current, making the current more, but this voltmeter reading keeps getting smaller and smaller and smaller, okay? Because in your circuit, so if we set up a battery, so here's my battery in the circuit, let's just put a thingy here, that's fine. There's my voltmeter. That's the voltmeter reading I'm taking, okay? That voltmeter reading is actually the external voltage of my circuit, okay? So as my current is increasing, that external voltage is getting smaller. And this is why. The equation we would look at is this one. My EMF equals current times R times little r, okay? My voltmeter is reading external voltage, and external voltage is I times big R, okay? So, as my current increases, okay, I times R is going to get bigger. Oh, no, it's the wrong way around. I'm telling you nonsense right now. Let's go here. This is what I wanted. Okay. This is a constant. This is what I'm trying to tell you here, okay, is that your internal voltage, which is I times little r, okay, if my current increases, my external resistance is getting smaller, okay. If my external resistance is getting smaller, then the voltmeter reading gets smaller. Also, if my current increases, then I'm losing more potential difference, I use it loosely, across the cells, because the internal voltage gets higher because there's greater current going through the internal resistor, and if your internal voltage increases, then your external voltage decreases. Okay, so there's a couple of ways around you can do it, but if my resistance is decreasing so that my current can increase, then my voltmeter reading must get smaller. But essentially, it's because this reading is getting bigger, okay, because internal resistance is a constant. Now they ask, which group, either 1 or 2, use the battery with a greater internal resistance? So you look at this and you go, well, the gradient of the graph represents resistance. So the steeper the graph, the higher the resistance, which means just looking at it, that means group 2 has the higher internal resistance. So that's group 2. Okay. Now, same question. Now it says to you, use the graph to determine the EMF of the battery used by the learners in group 2. Well, you know, we actually did that straight away. Look, 12 volts. Okay, so my EMF is 12 volts. Great. Now it says, calculate, make sure you get the right values here. Calculate the internal resistance of the battery used by learners in group 1. Okay, so guys, you cannot use EMF equals I times R plus R. I'll try not to throw things around the studio, shall I? Okay, because I don't actually know what the external resistance is. But I've already said to you that my resistance equals V over I. Okay, so the gradient of my graph gives me internal resistance. Okay, so what I'm going to say is that I know that my internal resistance is my gradient, and gradient means that I take the change in my y value by the change in my x value. My y value is voltage, my y value is current. Has to say change in voltage over change in current, because it's a gradient. I've got to take two values and minus them from each other. So we go back here and we say, fine, you know what, I can take any two sets of values. Use ones that are easy to read off the graph, okay? So for example, we can use the 12 and the 0, because that makes sense. And then if we go over here, let's use this point here, which is 4 and 4, okay? So it's always, we're going backwards, so we're going to do, when I plotting my points, I'm going to go 4 for my change minus 12, and this becomes 4 minus 0, okay, and 4 minus 12 gives you minus 8 divided by 4, which gives you minus 2 ohms. Guys, does it matter that the internal resistance is negative? No, not at all. It's a negative gradient to your graph, okay? So it does not matter in the least that you get a negative answer here. And if you want to think of it this way, it's really telling you that the internal resistance has a negative effect on the circuit, if you want to do that, okay? But if it does make you happier, then write a little statement that says that internal resistance is 2 ohms. That is actually quite high, okay? I'm going to be honest with you. An internal resistance of 2 ohms in a circuit is actually very high for a battery, especially considering, well, it's a 12-volt battery, so it's okay. That's like a car battery, all right? If your battery had started with an EMF, say, of 3 volts, and you got 2 ohms as its internal resistance, throw the battery away. It's fairly useless, okay? Far too high internal resistance. Now, same question. If the internal resistance of the battery was negligible, in other words, you could ignore it, draw a sketch graph to show the shape of the graph when the voltmeter reading is plotted against the ammeter reading. Well, guys, this is for the battery, okay? So, first of all, I'm looking at voltage, potential difference, current in amperes. This is for the battery. We're saying ignore internal resistance, pretend it's not there, which actually means the voltage, the potential difference of the battery remains constant. It's a straight line. Be careful here, okay? Because you're going to be tempted to draw it at an angle because that's what you know. So it's got a slope because you know voltage over potential difference gives me a slope, but that's for a resistor, not for a battery. Okay, there is no internal resistance, and if you can't get a gradient to this graph because it's parallel to I. Okay, be very, very careful. Okay, now I know you're getting tired, but let's just quickly have a look at this problem, and then we'll go to a break and we'll actually solve it after that. But this is my favorite part, and this is such a nice circuit. So here's my circuit, okay? And they say to you that you've got 3 resistors, 2 ohms, 4 ohms, and Rx, are connected to a battery as shown in the circuit diagram. Brilliant. When the switch S is open, the reading on the voltmeter is 10 volts. Switch open, reading 10 volts. That tells me EMF equals 10 volts. I'm going to write it on my circuit. When the switch is closed, the voltmeter reading is now 8. Remember, as soon as I close the switch, that means my external voltage is now 8 volts, and the reading on the ammeter is 1 amp. Great. Now, first thing I want to do before I even do anything else is now I go through the circuit and I go, let me find the parallel and series sections of it, okay? So I go here and we take out our highlighters, which the boys hate because most of them don't have, but here we go. I'm going to start with yellow. I'm hoping you'll see basically my circuit's going to turn yellow. So the switch is now closed. So I get to this point over here. Okay, so I get to the 2 and the 4, and now the current has a choice. So some of it goes through the 2 ohm resistor. Okay, some of it goes through the 4 ohm resistor. Now I've deliberately done it in 2 different colors because with the resistors having 2 different values, the current will split unevenly. Okay, what's important to remember here before I move on, okay, is that if I put a voltmeter over the parallel section, both these resistors will have the same voltage, okay, but they have different current. However, once we get to the end, once we come to here, they all, oh, wrong color, that's not going to help me. They all join together, comes back into series again. So we've got Rx, okay, that goes through here. And basically what this tells me is that this 1 amp, okay, this 1 ampere of current is the current that goes through Rx because it is in series, okay? But Rx doesn't necessarily have the same potential difference as the parallel section because the external voltage is going to split up, okay? The fact that they gave me EMF and they gave me external resistance or voltage tells me, sorry, that I have internal resistance. I'm probably going to have to calculate it, okay? So we look at this and we go, I've got an idea of where we're going, and I think with that in mind, because we'll get halfway through a question and then we're going to have to take a break, so what we'll do is we'll take a short break, and then when we come back, I'll finish this off for you guys. Okay.
All right, then, guys, let us take a very quick break. As Tracy has said right now, we'll see you after this. Welcome back from that very short ad break, Mindsetters. We are really having fun in studio, and I'm sure that you're also having fun and trying to revise all of your work so that you can go there tomorrow and write and represent yourself, your school, the whole district, the department. You know how it works right here on Mindset. Right now, though, let's just get back to learning with Tracy.
Thanks, Pumi. Okay, guys, well, first of all, apparently we have over 50 questions on the Facebook page, so don't send any more in, because there's a limited time. We are going to get to as many as possible grade 12s, okay? So hang in there, stick with us. We're going to get to as many as we can, but please don't send any more in, because I don't think anyone's going to get there to help you with them. I'm sorry, guys, because it's only a few, there's so much time in a day. Okay, but we'll get through as many as we can. So let's just head into the electricity, which is great. And if the first question is write down Ohm's law in words. Once again, and now this is the third question we've done today, and this is the third law you've had to state. Okay, the potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. So potential difference across the conductor directly proportional to the current at constant temperature. Brilliant. Off we go. So now, look here. Calculate the resistance of unknown Rx. And now this is when we start going, that's nice, Tracy. I'm going to move on to the next question. Because we go, 7 marks. Don't worry about it. Guys, finding Rx really isn't so bad. Because if I know the voltage over Rx, then I can find Rx, but finding the voltage is probably going to be a little difficult. I do know my total current. I do know external voltage, which actually means I can work out the external resistance. I'm deliberately not doing EMF because I don't know what R is. And in fact, if we go further down on this question, it actually asks me to find R next. So that's how I know that perhaps I shouldn't find it in this question. So that tells me I'm going to need to use the external stuff, the V external, the R external, and my current. Because, watch here, okay? First of all, R external, my total external resistance, is equal to my parallel resistance plus Rx. Okay, so there's two things I need to find. First, I need to find the external resistance, and I need to find the parallel. External resistance is easy, because I'm going to go external resistance, external voltage, and my current. My external voltage, they said to me, was 8. My current was 1. We like it when they give me questions like that, because I don't need my calculator, and I get 8 ohms. Okay, so now I can put the 18 over here. Now I need to calculate my parallel resistance. Okay, so we're going to go, 1 over R parallel is 1 over R1 plus 1 over R2, which means here I've actually got 1 over 2 plus 1 over 4. Guys, I know some of you don't do so well with the fractions, but this actually gives me 3 over 4, but I'll show you. Okay, watch. Okay, and it's another one where you can do it. It's great on your calculators, because watch, if I go 1 divided by 2 plus 1 divided by 4, your calculator gives it to you as 3 over 4, which is great, okay? So we know that we get 3 over 4, but remember, this is 1 over R parallel. I actually need R parallel, so I'm going to go R parallel then is 4 divided by 3, and we get 1,33. Must be rounded off. Okay, so I get 1,33. So my R parallel is 1,33. I want Rx, so that means I'm going to go 8 minus 1,33, and I get 6,67 ohms. What am I trying to tell you here, grade 9? You're not grade 9s? Oh, that was terrific. Grade 12s is you do it step by step. One part of the question at a time. Okay, don't rush it. Spend the time. That's also why when I use all my colors, it makes it really easy for me to see what goes with what, because that's the issue here, okay? Now they ask you to calculate the internal resistance of the battery. There's a couple of ways you can do this, but probably, this is a 3-mark question, so they would want you to be using this equation. This is the simplest, okay, where EMF is 10, current is 1, your R, big R is 8. You've just worked that out. That's 8. Oh, no, don't close the bracket quite yet, and that's R. Okay, and what you're going to get here is that R equals 2 ohms. But what if you don't see that? Well, we can do it this way. Look here. Your EMF is also equal to my external voltage plus my internal voltage. So this is 10. This is 8. Internal voltage is I times little r. So 10 minus 8 is 2. I is 1. Owen, look there. R is 2 ohms. Okay? Always more than one way to do it. Mark allocation is based on the simplest. If it's worth 3 marks, you really shouldn't be doing more than one equation. Okay? I know sometimes that's hard, but you really shouldn't be. All right. Now they say, after a while, the 2 ohm resistor gets hotter than the 4 ohm resistor. Explain this observation. Now we're going, they're referring to heat. Heat means energy in circuits. Energy means work. So if the 2 ohm resistor is getting hotter, then the 2 ohm resistor must be doing more work. When we look at the work equations, work equals V times I times T. Okay. Work also equals I squared R times T. And work also equals V squared times T over R. Okay, but let's just go with the simplest one, and that's this one. For both the 2 and the 4 ohm resistor, voltage is the same, time is the same. Okay? The 2 ohm resistor, however, gets more current. The 2 ohm resistor gets more current because it is smaller. Current is lazy. Current will take the path of least resistance. So the 2 ohm resistor actually gets twice as much current as the 4 ohm resistor. So you could work it out if you wanted to, but you don't need to. Gets twice as much current. If it's getting twice as much current, it must be getting hotter because we're transferring more energy. Okay? If we did it with this equation, okay, yes, R is smaller for the 2 ohm resistor, but the current is bigger and then it gets squared. So the current makes a far bigger difference to how much energy is transferred than the resistance does in this case. If then we take this equation where we've got V squared times T over R, okay, so this one is W equals V squared T over R. For both resistors, V squared T is the same, okay? So this top part is the same for both of them, which means I'm taking the same number, and for the 2 ohm resistor, I'm dividing it by 2. For the 4 ohm resistor, I'm dividing by 4. So if I take the same number and divide by a smaller number, I get a bigger answer, okay? Which means here, I'm still going to get more energy for the 2 ohm resistor because it's smaller, okay? So this 2 ohm resistor is smaller, it gets hotter because it has more current going through it. Okay, that's the easiest way to explain it. Because it has more current and it's on for the same time. If the time between them was different, then it's a whole different story altogether, but they didn't ask you for that, and they're not going to change 2 variables, grade 12s. Be careful, they don't do that. They always keep something constant because they have to. Okay, so grade 12s. Last bit from me, because John's going to come in and do an hour of great questions with you. Get a good night's sleep. Make sure you know your definitions. Okay? Keep at it. You've gotten this far. You'll be fine. All your hard work is going to pay off. Okay? So keep going. All right? Don't stress. Don't freak out. But get a good night's sleep tonight, please. Okay? Don't study till 5 o'clock tomorrow morning and then go to school and write your exam, because then you're going to fall asleep. All right, so it's not worth it. I will see you guys on Sunday for the Chemistry Live Show. See you then.
Thank you so much, Tracy. It's been actually a very exciting show. I've learned a whole lot, and I'm sure that you guys at home can also relate to all of that. Thank you so much for tuning in, and for all of you guys who posted questions, thank you so much, because in the next hour, John will be joining us in answering all of those questions. So yeah, from us in the studio, it is bye-bye. We'll see you in the